Measure speed of sound in air using cross-correlation with white noise or MLS. There are quite a few methods to measure the sound speed, such as phase shift method, time difference method, standing wave method. In this video, we use cross-correlation method. The measurement theory is simple: speed equals to distance over time. Here is the measurement setup. It is based on the software, multi-instrument, which can be downloaded from our website at www.virtins.com or www.multiinstrument.com. We will use its oscilloscope, spectrum analyzer, and signal generator function. The hardware of the setup is a computer with a sound card with stereo inputs. Two microphones are connected to the left and right microphone inputs respectively. The two microphones are placed apart with a known distance. A speaker is placed along the line of the two microphones. If we generate a sound through the speaker, it will travel to microphone 1 at T1 and microphone 2 at T2. By measuring T2 T1 using cross-correlation, we can determine the sound speed. In order to identify the cross-correlation peak without any ambiguity, we will use white noise, which is non-periodic, or maximum length sequence, which is pseudo-non-periodic. Here we go. The distance between the two microphones is 60 centimeters. The left and right channels of the USB sound card are connected to the two microphones. The left channel of the headphone output is connected to the speaker. Start the software. Open the signal generator panel. Generate a 1 kHz sine wave. Adjust the input gain of the sound card such that the two captured waves have comparable amplitudes. Set the frame width of the oscilloscope to 100 milliseconds. Put the spectrum analyzer to cross-correlation mode. In multi-instrument, in order for the cross-correlation to be performed on the full oscilloscope frame width, the FFT size should be equal to or greater than twice of the record length. The current record length is 4,800, so select 16,384 for the FFT size. On the signal generator panel, select white noise. A peak time delay of 1.708 milliseconds is detected. We can use DDP Viewer to display it in a larger font. Click the DDP Viewer button. In the derived data point selection box, select peak CCF time delay _ of. We can define a user-defined data point to directly display the sound speed result in real time. Click the DDP Viewer button again, select UDDP2. Enter the mathematical expression, speed equals to distance divided by time. We could enter the expression like this. However, what if the denominator, that is, the measured time delay, becomes 0 somehow? To be on the safe side, modify it using the IFEQ function of the DDP Viewer. It means that if the measured time delay equals to 0 in any cases, a very small value 0.000001 will be returned by this function, or else, the measured time delay will be returned. This will prevent the potential division by 0 issue. Now, the measured sound speed is shown directly in real time. The advantage of using white noise as the test signal is that there is only one cross-correlation peak and thus it can be easily identified. We can also use maximum length sequence as the test signal. A few cross-correlation peak appears. This is because MLS signal is non-periodic only if its length is longer than the record length of the oscilloscope. Increase its length from 1023 to 16,383. Now, there is only one peak in the cross-correlation. We can also use a burst type of signal. Here, we generate in 10 milliseconds MLS burst every second. Click mask. Enter 0.01 second for its on period, and 0.99 second for its off period. Generate the signal. Adjust the trigger level so that the 10 milliseconds burst will be captured in every oscilloscope frame. Adjust the trigger delay, to ensure the entire burst waveform is captured. Change the test signal to white noise. The measured sound speed is still 351 meters per second. Change to sine burst. As you can see, the measured sound speed is not stable now. This is because that sine burst has many periodic correlation peaks, which make it difficult to find which one is the highest, especially when noise is present. Now, change back to white noise. Put a FM radio as an interfering sound source and see how robust this measurement method is. As you can see, the measured sound speed is very stable at 351 meters per second, demonstrating that this measurement method is very robust. Let's take a look at temperature now. 30 degrees Celsius. The standard sound speed at this temperature is also 351 meters per second. So the method present here is very accurate.
Verdin's technology. Turn a PC into multiple virtual instruments.